เขาซื้อเยอะแต่จะแชร์บางเรื่องคือรวมไปฝากอาจารย์ก็ฝากกันนะฮะไอ้มีแบงค์เป็นแบงค์ที่เป็นเกี่ยวเวนเจอร์เนี่ยก็สถานไปผู้นักคุณพวกเอาคุณสถานชอบมาฝากเงินพวกอาจจะมีเครือข่ายเด็ดเบิร์พวกแบงค์แต่ละแบงค์เนี่ยก็มีข้อดีอยู่เหมือนกันแบงค์ในการเงิน4,000 แบงค์คนเยอะแบบ4,000 แบงค์นะแล้วแบงค์เนี่ยก็จะจับจุดของตัวเองอย่างเช่นไอ้ตัวซิลเวอร์เกตเนี่ยเขาก็จับจุดเป็นคริปโตแบงค์เลยนะครับปล่อยเป็นเหมือนเป็นเปิดให้กับพวกคือทำไมเอ็กชแนนเนี่ยมาจ่ายเงินการเทรดเนี่ยอะไรเงี้ยโครงการจ่ายเงินนะมันก็เป็นรูปแบบ
Thank you so much, Dr. Sham. Okay, this is the informal. Okay. Good evening, Professor Dr. An. Okay, สวัสดีครับ and good morning, everybody. Today, I would like to invite you to join our special lecture from Professor Dr. Aijun An from the York University. Okay, my name is Pisanu Jiokun. I am the head of department of the Statistics Department, Faculty of Science, Chiang Mai University. Firstly, I would like to welcome our students and the colleagues and everyone joining us for the seminar event, which is one of the special events that we provide for our staff and the graduate students for the master degree and the doctoral degree. This time, Professor Dr. Aijun An from Department of Electrical Engineering and Computer Science, York University, Canada, will share her valuable research and experience. That is very nice topic, right? Okay. On behalf of the Department of Statistics, I would like to thank so much for our speaker, Professor Dr. Aijun An, for giving their valuable time to present her research and share her experience. I wish that this event today will be an inspiration to our students and colleagues to create and conduct the research with the higher standard in the future. Well, it is time. I would like to invite Professor Dr. Aijun An to give her special lecture for us. Thank you so much, Professor Dr. Aijun An. Thank you.
Yeah, thank you for the welcome message and for the introduction. It is my pleasure to give a talk at your department. It is my first time to give a talk in a mathematics department. I hope you guys can find something interesting in my talk.
Thank you.
Thanks.
Okay, thank you, อาจารย์พิษณุนะครับ before Professor An give talk, I will introduce Professor An again to some people who doesn't know about the biology of Professor An. Okay. Just a moment, please.
Would you like to share screen? I share it. I can.
I will share first. Okay, moment. Okay. 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 Okay, so welcome Professor Dr. Aijun An from Department of Electrical Engineering and Computer Science, York University, Toronto, Canada. So Professor Aijun An received her PhD in Computer Science from the University of Regina in 1997, and she was a research assistant professor at the University of Waterloo before joining York University in 2001. So her research interest is field of data mining, machine learning classification, clustering, and pattern mining. So another field is data streaming mining or topic detection from text, document, emotion, and sentiment analysis. Keyword search over graph and relation database or social media analysis recommendation and so on. So now he has heads of a brain lab in York University in data mining lab. So this is the group research of Professor Aijun An with the Professor Manos. This is the detail of about the brain lab. So the brain lab, we have the meeting weekly from Friday. So we have to talk about the research group about the criteria of machine learning and data mining. So this is the talk in York University that when I have the scholarship and I visit here. So I received this scholarship from Canada government and meeting professor and at Lason School of Engineering from Department of Electrical and Computer Science. That's why I invite Professor An to give the special talk at our university. So after I finish the scholarship, I invite Professor An to one a committee of my PhD thesis, and I finished last year. So for the next stage, after I get the first job in Chiang Mai University, I keep connection with Professor An to send some PhD student. In this time, our department sent Sukit Thongkairat, the second year of PhD applied statistics to apply the CIS scholarship again with Professor An at York University. So Sukit, can you say hi, Professor An?
Hi, Professor.
Okay, so,
Hi.
okay. So now I think today is a special day to invite Professor to give the talk about the time-aware subscription prediction model for user execution in digital new media, adaptive parallel mechanism for digital new media. So please welcome Professor Dr. Aijun An.
Yeah, thank you, Champ, for the nice introduction. Let me share my screen. And also thank you for inviting me for giving this talk. It was my pleasure. So today, as the Champ discussed, I basically will talk about the two pieces of work we have done under this general topic, which is called the user acquisition and engagement in digital news media. As I will describe later, it is a part of our collaborative project with a newspaper in Canada, Global and Mail. Okay. So Champ asked me to introduce my lab first, so I prepare a few slides, so maybe overlap with what Champ has talked about. So our data mining lab at York University was established in 2002, right after I joined the university. And we conducted research in data mining, machine learning, and the natural language processing. And we have, since 2002, we have graduated over 40 PhD and master students. And also we have had more than 10 postdoc fellows. And currently we have 2 faculty members, me and Manos Papagelos. And currently we have 3 postdoc fellows and 7 PhD students together from me and Manos. And also we have more than 10 master students and some other research assistants. And here are the general research area and the topics under each area that we have been working on. So we mainly work on data mining, and under data mining, we work on pattern mining, data stream mining, and graph mining. And data mining highly overlapped with machine learning. So we're working on actually the data mining algorithm and also machine learning algorithms. But in particular, under the area of machine learning, we work on distributed deep learning and reinforcement learning applications. And in the past few years, we have been working on natural language processing projects. In particular, we work on sentiment emotion analysis in text, and also question generation from text. And we're also working on conversational systems, such as a chatbot, okay? And also we're working on graphs. A lot of data present themselves in the form of graph. So we're working on how to represent graphs. We're particularly working on dynamic graph embeddings, and also how to create knowledge graphs, how to create and use knowledge graphs. So those are the general research areas, and our lab receive funding from different agencies. We receive funding from federal agencies such as NSERC. NSERC is the biggest funding agency in natural science and engineering. So we have a variety of grants from NSERC, and we also have a grant from CERC. CERC is social science, and social science is supporting social science projects. Okay. And we're also funded by provincial funding agencies such as Ontario Research Fund, Ontario Centre of Innovation Grant. And more importantly, we connect with industry quite closely. So our project supported by industry partners such as IBM, Indigo, the Global and Mail, DataSouth, and so on. Okay. And currently, we are working on a few projects with most of them with industry, such as I'm working with IBM on GPU resource scheduling for distributed deep learning. And we're also working on data migration, how to move data from one location to another location in the internet. So this is also IBM supported project. And we're working with Indigo on a natural language processing project. In particular, we're still working on question generation from text. And recently, we're working on policy extension for question answering. And we also have some computer vision projects, such as image super resolution. And also the last project I listed here related to COVID. So there's a federal NSERC project that we working on. Particularly, we working on a sub project for signal detection of infectious disease from social media. Okay, and we have worked on quite a number of projects before. The one that I'd like to mention is the one that we work with the Global and Mail on data and visual analytics for decision making in news media. And this is the project I'm going to talk about in today's talk. And we're also working on some other projects with other companies. And I'd also like to mention big data research and analytic projects. Sorry, I forgot to use the screen. So this one, in particular, I'd like to mention this project called BRIN. And this BRIN project was funded by ORF, Ontario Research Fund, and this is a big project, and because it involved 4 universities, York University, and 3 other universities in Toronto. Totally have 4 universities. So we involve all of them, and we have like 12 companies, private sector partners working with us, and also for other public sector partners. So this project runs for 6 years, and the Global Mail project I'm going to talk about also partially funded by this grant. And so as I said, I'm going to focus on to talk about some of the work we did with the Global and Mail. What is Global and Mail? Global Mail is the national newspaper in Canada. Okay, it is the largest newspaper in Canada. It connecting more than 70% of Canada's population. And the project we're working with them is called Digital and Visual Analytics for Decision Making in News Media. Okay, And the 2 universities involved in this project. So York is the leading university. So we focus on data analytics, and OCAD University, it is fine arts school. They focus on visual analytics. Okay. And for the data analytics part, our focus is on user acquisition and engagement. And today's talk, I'm going to focus on what we did for user acquisition and engagement. Okay. So the general motivation for this project is that generating revenue has been a significant issue for online newspapers, especially in the past 15 or 20 years, because the newspaper has moved from a printed version to the online version. And there are a wide variety of different news media available for users. So there's a lot of choices. Okay, some of them are free. So therefore, in order to abstract readers and so that they can subscribe to newspaper is a very challenging task. Okay, and this is very important because subscription is still considered to be the major income for online newspapers. So there's 2 sources of income for news media. One is advertisement, and the second is users subscription. So at the beginning of online newspaper, a lot of major agencies, they provide free content, but soon they realize that only depending on the income from advertisement is not enough, because that kind of source of revenue is unstable. Especially, for example, when the COVID pandemic started, a lot of companies withdraw their advertisement, so their revenue decreases significantly. So they are heavily affected by the situation of economic. So in the past few years, those major newspapers moved heavily rely on subscriptions, and they have realized that getting users to subscribe to newspaper is a very critical issue for them to survive. So in order to get online subscriptions, then they must have some effective strategies for user acquisition and user engagement. Okay, so how do we identify potential subscribers? And how to promote the positive experience of the user. So those are the important issues for user acquisition and user engagement. However, the previous business models, before we tackle this issue, and they did not consider those, did not satisfy this demand. Okay, so the objective is to get a user to subscribe the newspaper, and so however, to do so is not a trivial task. So we must build a strong relationship between the reader and the newspaper, and this is not an easy task in this competitive world of digital media. So most of the previous work who try to attract users' attention is on news recommendation, how to build the news recommender systems. So at the beginning of our collaboration with the Global and Mail, in the first few years, we're purely working on news recommender systems. So we build a different type of news recommenders algorithms, such as high utility-based recommendation, topic-aware recommendation, or emotion-aware recommendation. So we built quite a few systems for them, and some of them have been incorporated in their hybrid news recommender systems. However, only doing news recommendation is not enough. Understanding and predicting engagement has not drawn much attention in the news domain, but they are very important. So for example, identifying attracting potential subscribers, if we can do so successfully, we can maybe do a targeted marketing so that we can increase the chance of users' subscription. Okay. However, such issue has not been dealt with before. So the general objective of our project is to design new ways to measure, to predict, and to promote user engagement and subscription. And we would like to use data mining and machine learning techniques to do so. Okay, so basically we try to analyze the user behavior data, that means what they do in the news portal, and then using machine learning and the data mining models to build techniques to build some models, so those models can support decision making for the news media. Okay, so what we have done in this regard? So yeah, in the project. For user acquisition and engagement, as I mentioned, we have done built some news recommender systems, and these have been, we have published, those are our publications for the news recommendation models that we built. And we also have proposed some predictive model for article dwell time. So dwell time of article is how much a user spent on the article. Okay, so it is important if a user spend a lot of time on the article, that means he's really reading the article instead of just clicking the article by chance or to see how is it, right? So we have proposed some algorithms to predict the article dwell time. Okay, and this is the first time ever people propose a model to predict the dwell time. And we proposed the problem and proposed the algorithm for solving this problem. And this work was published in NACO, which is a top-tier conference in natural language processing. Okay, on the acquisition part, we have proposed a time-aware user subscription prediction model, and this is at the time we proposed this model was a new problem to tackle, and we proposed this new problem and the solution to this problem, and it was published in a major data mining conference, SDM, in 2017. Okay, and another piece of work is adaptive paywall mechanism. And adaptive paywall, I will talk about what is adaptive paywall later on. So before we propose this work, all the paywall from the online newspapers, they using fixed paywall. So we are the first to propose adaptive paywall and propose a solution to build adaptive paywall. And this piece of work was published in the top data mining conference, KDD, and also the major journal in data mining, which is IEEE transaction in knowledge and data engineering. Okay, so today I'm going to talk about these two pieces of work. I picked these two because I think they are related to statistics. Chamber asked me to present something related. Yeah. Okay. So let's see. So my first topic is a time-aware subscription prediction model. Okay, and this work was basically part of the PhD thesis of my PhD student Haidar Dawoodi. He collaborated with another PhD student of mine, Motisa Zehayat, and to build this model. Okay. And so the objective of this part of work, the goal is to identify potential subscribers and predict the subscription time of those potential subscribers. Okay, so that's the general objective. And this type of system is useful because if we can identify those potential subscribers, we can do targeted marketing, right? You can maybe get coupons, promotions to these potential subscribers so that they are more likely to subscribe the paper. Okay. And before we propose this problem to predict the potential subscribers, there was no work on it. And of course, there's no algorithm to address this problem as well. However, this problem is quite challenging. So yeah, this is first because a decision for subscription is under the influence of many factors. For example, demographic factors, such as the age, the education background, their income level of the users, and their social factors, and also their cultural background. And also, of course, it's related to past experience of the user with the news portal. When they read the news before, what's their experience, right? If they like the newspaper, they are more likely to subscribe. So those are the factors we believe determines whether user will subscribe or not. However, there's no domain knowledge to relate those factors with the decision to subscribe. Okay. And also, even those factors are important, but usually we don't have those information about the users. Their demographic information, their social and cultural backgrounds. Usually we don't have such information. And the things that we have is their past experience in the news portal. Okay, so what do I mean by past experience? Past experience are measured by the user behavior data. So what is user behavior on the news portal? So this is news portal interact with the user, right? Whenever user come to this newspaper to read, and they make a clicks, right? Click on articles or click on whatever, but each click is called a hit. Okay, so the news portal knows what articles the user read and what time they read those articles. So those data are called user behavior data. Okay, so we have those data the agency collected. So we can do purposizing and analyzing them. Okay. And we can get engagement measures. That means we can, based on this data, we can measure how much the user engaged with the newspaper. Okay, and based on this, those type of data, and we build the time-aware subscription prediction model. Okay, so this is our whole framework. So we collect data. Based on those data, we try to relate the user engagement measure with the time of their subscription. Okay, and then this model is, when the model is built, we can use it to predict for the future user, for another user, whether they will, how likely they will subscribe the newspaper. And further, what would be the estimated time they will do the subscription? Okay, so that's the general framework of in building this subscription prediction model. Okay. So our model is built based on the user behavior data. Let's look at a little bit detail on the user behavior data. So the user behavior data are basically click strings. Okay, so each string contains a sequence of hit. When the user visits the newspaper, they click different articles. That's a sequence of hit. Okay, and each hit contains the date and the time of the user visit or click on that a particular article, and also the user ID. If the user is a subscribed user, we have its user ID. And also user environment variable, that's the IP address of the machine the user is using to visit the news portal. So for unsubscribed user, we basically identify them using the IP addresses. Okay, and we also know the browser time, the visited article, of course, right? And also the special event. If the user hit the subscription and pay for it, then it's an event we recorded, what time it is occurs. Okay, so so we want to build a model based on those data to predict the user subscription likelihood and the time, right? So and we think that the users, whether the user will subscribe and the time it subscribe related to the user engagement, the degree of user engagement to the news to the portal. Okay, so what is user engagement? User engagement can be described as the positive aspects of user experience when interacting with the system. Okay, again, we think there's a strong relationship between the degree of user engagement and subscription. So therefore, at first, we should get the user engagement measures for each user. Okay, so what are the engagement measurement we use? We identify two types of user engagement measures. So the first one is frequency-based. Frequency-based, we call those features, frequency-based features. So the second is time-based. So there is a number, a few frequency-based measures. For example, we have the total number of articles the user read during a period of time. So this is called frequency-based. This is one of the frequency-based measures. And also the average number of articles per user's visit. This is also frequency-based measures. Okay, and the time-based measures is the first one here is the average dwell time per article. That means the dwell time is the time spent by the user on the article. Okay, and we also use the average dwell time per visit, per user session per visit. Okay, with one visit, the user can visit a few articles, and also the total dwell time of the user for a period of time. So we identify those measures as user engagement measures. Obviously, the higher of the value of those measures, the more engaged the user with the portal. Okay, so we call these engagement factors. So having those engagement data, and we also knows for each user whether they subscribed or not during a period. We call this period exploration period. Okay, so in this period, some users become subscribers, and some users become never subscribe. Okay, and for the subscriber, we know what time it subscribed, and for non-subscriber, we know that the first time it visit and the last time it visit, but it never subscribed the newspaper. Okay, so given such data, our goal is to estimate the cumulative distribution function, which is the probability of t less than t. So this small t is the time passed after the user's first visit during this period of time. Okay, and we try to build this CDF function for every user and with respect to a subscription time. Okay, with t, again, the small t is time passes after the first visit during a period of time. Okay, so in order to get this CDF function, we have to know the distribution, the density function, right? So we assume a Weibo distribution for time t. So Weibo can be expressed using this formula here. Gamma is the shape parameter, and alpha I is the scale parameter. Okay, so I means corresponding to i's user. Okay, the user I. Okay, so we assume this density function is have the same shape parameter for all the users, but a different user have a different scale parameter. So we choose a Weibo distribution because it's a flexibility. It can model both right-skewed or left-skewed and even the symmetrically distributed data. Okay, so assuming this distribution, then the CDF can be expressed using this formula. So again, we have the shape parameter is the same for all the users, but for different users, we have different scale parameter. Okay, and we further assume that this scale parameter for a user related to its engagement factor, engagement measures. Okay, so xi is engagement measures that we talk about in here. So yeah, so xi is the vector of those values. Okay, for ith user. Okay, and the B here is the coefficient vector. Okay, T means the transpose. Okay, so basically we use a generalized linear model to model this alpha I and relate it to the engagement factor. Okay, so so if you plug in this AI into here, then the parameters in this function is B and gamma. Okay, the unknowns are B's and the gamma. So in order to build this function, we need to estimate this B vector and a gamma from the training data, a set of training data. Okay, so what is our training data? Again, we have n users, n data points, right? Each point corresponding to a user. For each user, we have xi, their engagement factor, right? And we also know if the user is a subscriber in this period, we know it's a first visiting time, it is a subscription time. Okay, this one is subscription time. So the difference, the period, the length of this time is ti tilde. Okay, and for non-subscriber, we know it's the first visiting time, it's the last visiting time, and never subscribe. So we know this, the length period is t bar I. Okay, then therefore, given such data, we try to formulate our problem as a log likelihood optimization problem. Okay, so we try to find the those CDF by optimizing this function. This is our objective function. Okay, so here n is the number of data points, number of users. Okay, I is the indicator function. So I equal to 1 means ith user subscribed the newspaper, and 1 is equal to 0 means that user I did not subscribe. Okay, so here, so if we try to maximize this, that means that if the user subscribed, we try to optimize this log likelihood. And here, because this is for basically for the subscribe user, and the TI for the subscribe user is this period. It's the time it taken for the user subscribe the newspaper. And when the I equal to 0, then this becomes 0. So we try to optimize, maximize this one. And here TI is the time, the time period that the unsubscribed user visit the news portal during the exploration time. Okay, and because we know before this time the user did not subscribe, so the probability is 0. So we try to maximize the probability after, maximize the probability, this probability. Okay, because only after that it's a likely user will subscribe the newspaper. Okay, so we formulate our problem is this log likelihood optimization problem. Okay, so this is our objective function. Then, so our purpose is to find again find the B and the gamma, right? And how do we do so? This is our algorithm, our learning algorithm. Okay, so this algorithm is a gradient ascent algorithm because it's a maximization algorithm, and we first initialize those B's and the gamma, B's randomly and gamma initialized to 1. And then we use a coordinate ascent method to learn B and gamma iteratively. Okay, so in each iteration, we try to update B using the partial gradient of the loss function with respect to B. Okay, and after B is updated, we use this updated B and the previous gamma to update gamma based using the partial derivative of the loss function, which is the loss function is objective function, right? With respect to gamma. Okay, so we do this iteratively until the parameter converges. Okay, or until the maximum iteration has been reached. Okay, so that's how we learn this function. Okay, using this gradient ascent algorithm. So so after this function is learned, this is the function that we are trying to learn, right? When the gamma and the B is in here, B is in here, right? So after we learn this function, we can use this function to predict the subscription occurrence, whether the user will subscribe or not. Okay, so it is easy to use this one. Okay, so given a new user, okay, we know its engagement vector from its history. Okay, and then we can calculate AU using those B and XU, and then we know gamma, right? So we calculate the probability that the user will subscribe at the time t. Okay, using this SDF function. And if this probability is bigger than 0.5, then we predict the subscription is going to occur, okay, at the time t. And in order to estimate what time the user is more likely to subscribe, then we use the median of t. So this is the how we calculate a median based on Weibo distribution. Okay, so based on gamma and AU is based on B, right? So that's how we predict the subscription time. Okay, so that's how our method works, and we of course need to evaluate the proposed method. So we use the global mail data in this period of time, and in our data set we have more than 17,000 subscribers and 71,000 non-subscribers. Okay, and this is our training data, and we use tenfold cross validation. That means we use 90% of them as training, 1% of them as testing, and we do it 10 times, different times, have a different training and testing split. Okay, so so here is the result. So this is to predict whether subscription is going to occur at different t values. Okay, and we compare our methods called the time-aware subscription prediction, so TASP, and we compare with other classification prediction algorithms. The first one is GF48, is a descent tree prediction algorithm, descent tree learning algorithm. And LR means logistic regression. And then this is a naive Bayesian algorithm. This is random forest. So so as this at a different time point, so you can see that the performance measure is F measure. Okay, so you can see that the proposed measure has a higher F score than all other measured on all these evaluated time point. Okay, so so that's one result for occurrence prediction, and we also evaluate subscription time prediction. So here, because it's a regression problem, so we use a mean absolute error to measure the performance. And here we compare our TASP algorithm with average algorithm. So this average algorithm is basically using, let's see if we evaluate at this time, what is the performance algorithm. Using average algorithm, we basically using, at this time, we have seen a few users. We use their average subscription time to predict the new user. Okay, so you can see the performance is not really good, but our performance is much better. The error is lower than this baseline. Okay, so so that's the subscription time prediction. Okay, so to summarize our contribution in this area of this topic, we defined the new problem of time-aware subscription prediction for user acquisition news media. And we propose some effective user engagement measures. So those measures we actually evaluate, my students evaluate to see how good they are. They are actually better than something else they have used alternatively. Okay, so using this engagement measure to predict the user subscription is soon to be successful. And we also develop a novel probabilistic model to predict the user subscription occurrence and the time of subscription. And our empirical evaluation shows the effectiveness of the proposed model, which is better than some baseline models. Okay, and this model can be useful to recommend trustworthy potential subscribers to the news agency so that they can do some marketing, directed marketing based on the prediction. So that's my first topic. So I pose 4 questions, or can I continue?
Okay. So in the first talk, any question for Professor An? Okay, I will ask first. So Professor, could you go to the slide about the Weibull distribution?
Yes, sir.
Okay. Yeah. Okay. We have the question of the audience. So does this prediction similar to churn prediction?
Oh yes, I think the churn prediction is the other direction, right? Predict what user you will disconnected with a business, right? Will end their business with a company, and here we predict likelihood of a user will join this business, will become the customer business. So it's certainly have a relationship.
Oh.
Right, that's a good question.
So can we change another distribution? In your opinion, is if we not choose Weibull? Because I want to know that why you use Weibull distribution for subscription.
Oh, yeah, just because of its flexibility, it can model different shapes of distribution. We choose it purely because it's flexibility. Yeah, if you have something better, let me know. I'm not statistics.
Yes. Okay. Okay. Any question? Okay. So what is the continue about for the next project about this topic? Or we can use another data.
If we continue this direction, Yeah, of course, it applies to other data set as well, right? So as long as you have the user, the click strings, right? The user behavior data, you can, yeah, it's applicable to other data set, right?
So if our student who interest this topic, what is the knowledge background about to prepare to do this research? How about the background about the subjective in computer science or statistics? If who want to interest your topic.
I think this is more like a machine learning, right? So it's basically we formulate, you know, using this formulate a function, right? And we need to the prediction function. We need to estimate the parameters in this function. And how do we do so? We're using the machine learning algorithms. This ascent the algorithm. So yeah, as long as you understand this, yeah, it should be. Yeah, not difficult to understand the whole process, right? Yeah.
Okay. Any question for us to Professor Aijun An? Okay, I think okay, we can move to the second topic. So,
Yes, sir.
Okay.
Yeah, certainly you can ask. Anyone can ask at the end, very end.
Moment. For the ones of the last question for the first talk. I want to see the result again about the T. What is the unit of T that you measure the previous slide?
Oh, so this is the unit of T is days. We're using the day scale, right? So this is for 8 months period. We use the day scale, and then the day 15 after the first the visit of the news portal for a user, what would be the particular user, that particular user, whether they are likely to subscribe or not, right? So those tier the in day scale.
Okay, thanks.
Okay, no problem. Okay, so right, let's move to the second topic, which is adaptive paywall mechanism for digital news media. Okay.
Professor, we have the last question again. So, why you choose MAE instead of MSE?
Yeah, that's actually a question I want to, I just ask my student, Haida, why you choose MAE instead of SSE? Yeah, sorry.
Okay.
So he is the person who did this work. Yeah. So any particular reason for choosing mean absolute error instead of MSE? Sorry, I can't answer you. Yeah, I hope he's here. Yeah. So I guess maybe it's better check with him to see what's his thought on it. Yeah, okay. That is a good question. Yeah, when I prepared the slide, say, oh, why you use MAE?
Okay.
Okay, so let's move to the second topic. So this topic is also majorly done by Haida as a part of another chapter of his PhD thesis. He has 2 more chapters, so there is one presenting 2 of his chapters, and also collaborated with Moti Hayat, another PhD student, and the Golden Idol is from Global Mail. It is their director of their data science department. And so the motivation for this topic is that, as I mentioned, online newspapers rely on subscription, right? So they generally provide some certain amount of free articles for each user to read for non-subscribers. Okay, so when usually they provide a fixed number of free articles for them to read. So after the user reads that number of articles, they will present paywall to the article. So this is examples of paywall. Okay, so when the user click at the next article to read, and instead of presenting article, the news portal present the information requesting them to subscribe, to pay for it. Okay, so so such cases are called paywall. So the purpose of presenting paywall, of course, to promote the user to subscribe, right? So hopefully user will subscribe to the newspaper. And again, before we're working on this topic, almost all the news agencies, so I can say almost all, use a fixed paywall. They provide a fixed number of free articles for a user to read in a certain period of time, such as a month. Okay. However, the purpose of presenting paywall is for user to pay, right? However, there's no correlation between the number of paywalls presented to the reader and the number of subscriptions. So this is what HEDA analyzed. There's no correlation. So therefore, we proposed adaptive paywall. Okay, so it does not mean the more you present, the more likely the user will subscribe, right? So we present this adaptive paywall. Hopefully this one can automatically determine at what time during the user visit, during a user session, the paywall is presented. Okay, so that's why it's called adaptive. It can automatically determine when to present the paywall based on the user's past behavior. Okay, so and we in design this adaptive paywall, we try to maximize this objective function. Okay, so K is the number of articles the user has visited, let's say in this session. Usually the paywall present to the non-subscribers, right? So and we saw different sessions, visiting sessions could from a different subscriber. We don't have the IDs, so usually we talking about a session, right? So K is the number of articles the user have visited in this session. And phi AI is the utility of article AI, okay? And this psi AI is the cost of article AI. So what is utility? Utility is the usefulness. You can say the usefulness of this article in terms of persuading the user to subscribe, right? So for example, we can use the number of users who subscribed after seeing this article as a utility, or the time the user spent on this article as a utility. The more time spent on this article, the more engaging this article is, right? So, and the cost of article can be, for example, can be the amount of money the agency spend on to pay to the author of the article, right? So the cost of the article, or in our experiment, we don't have the cost. We use the length of the article. The longer the article, the more costly the article, right? So we can define the utility and our cost differently. Okay, so this objective function is to maximize the sum of the utility of the articles the user have visited divided by the sum of cost the user have visited. Okay, so that's the objective. Before we present in the paywall, we want to optimize this function. Okay, so here is a illustration of adaptive paywall. So here each node is an article. Okay, and here for each article we have the star means is a utility, L means utility is low, and the dollar means is cost, M means the cost is median, etc. Right? We have a utility is high, cost is low, etc. Okay, and this solid line means user 3's visiting path. Okay, user 3 visiting these 4 articles, And this dashed line is user 1 visiting these 4 articles. And this dot and dash line, it means user 2 visiting those articles. Okay, so if we use a paywall, let's assume that the number of articles we allow user to read is only 2, then the paywall will be presented here for all the users. Okay, so it's fixed. But to get adaptive paywall, we determine when to present the paywall to each user depending on their previous visit. Okay, previous visit. So we presented here because it maximized the sum of utility of this article divided by the sum of cost of those articles. Okay, so it's a personalized paywall. It's determine what you have visited. Okay, so so that's the illustration of this paywall there. Okay, and how to determine where to present the paywall is actually not easy. It's it's not a trivial task. And first, how do we incorporate the utility and cost our articles in this optimal decision making process? It's not a trivial task. And what we know for this task, we only know the articles the user has visited and the articles, the next article the user is trying to read. Okay, the article beyond the next one is unknown. We don't know what if we allow the user to read, what will be the other actions the user is going to take. After that, we don't know. Okay. And we want the model to be flexible. That means that the utility and the cost can be defined by user in their desirable way. Okay, and also because the paywall decision is online, so the decision making has to be fast. You cannot do like a long-term optimization to get an optimized solution, right? So the decision has to be fast. Okay, so so to address these challenges, we made, this is our contribution in this paper, okay? So we were the first to propose the adaptive paywall mechanism in digital news media, okay? So later I will mention that Global Mail and have adopted this idea. They developed this idea further, developed the idea into a dynamic paywall, and they are using it. And they have won some media award because of their dynamic paywall mechanism. So, but we were the first to do so. Okay, and they are the first agency to do the dynamic or adaptive paywall. And we cast this dynamic paywall problem into a sequential stochastic optimization problem. So the decision problem is actually the sequential decision making problem. Okay, and we do it in a principled way. And we propose data-driven solutions to solve this optimization problem. Okay. And we, of course, evaluate this method to the real data set from the Global Mail and demonstrate it is better than some other baselines we can think of. Okay. So, so let me first illustrate this sequential decision-making problem. Okay. So we have a user who have visited K-1 articles in its current session, and it requests to read article AK. Okay, and our paywall model has to determine whether to allow its reading AK or to present the paywall. Okay, present paywall. So this decision, binary decision. Okay, and if we allow it to read AK, then the user will likely to request another one. Okay, and then we need to determine whether to present the paywall at that time or continue, like user to continue reading. So this is a sequential decision-making process. Okay, so in order to make this decision, what do I have? What the information that we have? the first one, the main information we have is navigational graph. Okay, so what is this graph? This graph here, each node in this graph is an article. Okay, article, and from this article to this article, we have a link. It means that after, we have the data to show that there's at least one user visiting this article after this article. So then we put a link, okay? And we have a weight for this each link, with basically say the percentage of the users visiting this node, visiting this article after reading this article, okay? So let's say we have two links here, so those two, you can see the probability to add up to 1, right? Yeah. So basically, those navigational graph was built from the user visiting history. We have the previous user sessions on those articles, so therefore we can use this information to build this navigational graph. Okay, and this is the information we know to build this paywall model. Okay, and of course, because we want to optimize the sum of the utility divided by the sum of cost, right? So we have to have a utility model, we have to have a cost model, those formulas. Okay, so those are the input to this paywall model. And based on this input, we need to make decisions. Okay, so this is our framework and the problem statement. And to present our adaptive paywall model, and let's see its components first. So, so the first component is the state variable. Okay, so the state at the time t equals to this ut bar, ct bar, and at. So at is the article the user requested at time t. Okay, and this u bar t is the sum of utilities of the articles the user has visited and requested in this session, in the current session. Okay, so that means all the articles that the user visited, the sum of their basically is, I already say that. Okay, and the c bar t is the sum of cost of the articles the user has visited and requested in this session. Okay, and the second component is a decision function. Yeah, which is defined like this. So we need to make a decision whether to present the paywall or not. So this xt is either 0 or 1. So 1 means that the decision is to present the paywall, and 0 means that we do not present the paywall. Okay, so this pi is the policy. Policy it means given this state, okay, given this information, whether we need to present the paywall or not. Okay, and the third component is transition function, which is to convert one state into the other, the next state. Okay, given the current state at t and the action either present the paywall or not. And also the next requested article, and this function converted into the next state. Okay, so if xt is 0, that means paywall is not presented, and then in the next state, the at plus 1 is the article the user try to visit. Okay, and u bar t plus 1 is basically this is the sum of utilities, right? So you're just adding up the utility of this requested article into ut plus 1. Okay, the cost is basically adding the cost of a new requested article into ct plus 1. Okay, but if the action is 1, okay, that means the paywall is presented, then in the next state, at plus 1 is just a paywall. Okay, and ut plus 1 ct plus then the same as the previous ut, same as ut and ct respectively. So that's a transaction function, and the contribution function is like a reward function. So if given the state and it's a current action, if xt is 1, that means the paywall is presented, then the contribution function, the contribution value of this action is the sum of the utilities, take away the requested one, because the paywall is presented, requested one is not presented, okay? And divided by the sum of costs, take away the cost of the presented, the requested article, because the article is not presented to the user. Okay, so basically this is the result. The sum of the articles the user has visited, sum of utility of articles the user have visited, divided by the sum of cost of the articles the user has visited. And we have this 0.05 is just to avoid, simply to avoid zero division. Okay, so but if we allow the user to continue this is 0, then the contribution is 0. Okay, so we do not give this contribution because when the paywall is presented, its contribution consider the previous articles utility and the cost. Okay, so we do not giving multiple times. Okay, so yeah, so we give the reward at the end. Okay. So so that's the components of this model, and we formulate this paywall decision problem as to find a policy, okay, so that this some of the contribution values are maximized. Okay, so here T from the beginning time until the end, until the paywall is presented. Okay, so gamma is the discount factor. Okay, so usually is less than and equal to 1, which is to like the future contributions to be less important as the current time contribution. Okay, so we maximize the sum of contributions in these sequential steps. Okay, we try to find a policy to do so. Okay, so that's our problem definition. We try to find this policy. Okay, and maximizing this function is the same as maximizing the value of state st. Okay, so the value of state st is defined using the expected value of still the sum of the contributions at a different time point starting from st, and the different time of the decisions made by this policy pi. Okay, so and this can be written as let's say st is the initial state. This can be written as the contribution of this contribution value at st given the condition using given the action using the policy pi time plus the expected value of the state of the next state. Okay, so given st and this action. Okay, gamma is the discount factor. Okay, so this one is the same as the objective function in here if we assume st is the initial state. Okay, and so objective to find a policy to optimize this value. And this, according to a Bellman equation, there is optimal value of this state value based on the optimal policy is equals to the maximum value among st equal to 0 and 1. The maximum value of this. Okay, so here is the contribution value of st given ST value, and this is the optimal value for the next state. Okay, and xt equal to 1, xt equal to 1 means the paywall is presented. Okay, and this one becomes 0. This one is not considered. When st equal to 0, this one is not considered. The value is equal to the maximum value, the value of st plus 1. Okay, so then how do we fund this policy? If we one way to do so is to do dynamic programming. However, our state space is continuous. Okay, so the transitional method value iteration it cannot apply. And another method which is popular right now is to use reinforcement learning to learn the value function. Okay, to learn this value function. But that required the representation of articles, the features of articles. Okay, and so we actually later using reinforcement learning to learn this value function. But before we did that, we think about we designed another method called look ahead policy method, which is basically using. Based on sampling method, we try to look ahead what's going to happen next after we either allow the user to continue to read or present, continue to read what's going to happen. Okay, so so basically this this algorithm is to given a current state and the navigation graph that I already described, we need to determine the action xt, so whether to present paywall or not. Okay, so this is the object, the objective of this action. The procedure is, as I mentioned, is sampling based. Okay, so basically we first randomly generate a set of paths from the navigation graph, starting from AT, from this article. Okay, so so we have the navigation graph over here. Okay, so let's say if we start from AT and we try to randomly generate some paths based on the weights. We treat those weights as probabilities. Okay, so we randomly generate some paths. So each state we're using the probability of on that edge. Okay, and the path, the maximum path, we set a parameter as the maximum length of path, which is h. So that means the path can contain a maximum of h nodes, h articles. Okay, and also if when we reach on certain nodes, let's say if we, for example, reach these nodes, and for example, let's assume that this node has many links to different nodes, and their probability, each probability is quite evenly distributed. That means that the probability is quite uniform, and we consider the entropy of this node to be high. Okay, so we use the entropy measure to measure a node. If the entropy is greater than I think the entropy is greater than 0.5, we stop, not less than. Entropy is greater than 0.5, we stop growing the path. Okay, stop growing the path. So so the path can be h length, contain h node could be less than h. Okay, so so after we generate a set of paths, then our objective is to determine whether to present the article or present the paywall or not, right? So we made that determine based on those randomly generated paths. So how do we do that? Based on each path, we find a time point so that the discounted, it's a discounted contribution is the highest if we present paywall at that point. So we present paywall here, so we present paywall here. Okay, so and then when we can because we know those articles, we can easily calculate that, right? So we record the highest contribution, highest reward for this pass. Yeah, the highest contribution. If you find that point contribution is the highest contribution. Okay, and then we do it for all these paths in this set of paths, and we calculate average contribution of all the paths in this set. Okay, and then we calculate we try to compare if we present paywall at this state, the contribution that we obtained, whether it is greater than the average contribution of all these paths. Okay, those paths is to allow user to navigate, right? If it is greater, then we present the paywall. If it's not, then we let the user to continue to navigate, to read articles. Okay, so this is this is basically the algorithm. It's based on the look ahead policy, and the look ahead is based on this navigation graph, based on random sampling from this navigation graph. Okay, so that's basically the algorithm. Okay, so in this way we avoid the expensive optimization procedure to find the best policy. So this is we find approximate a good part. It's like approximate optimization, find a good policy. So sampling. Okay. And in order to see how good this method is, then we do the evaluation using the global mail data set. And so again, we use the click strings. Okay, and we have more than 4 million, close to 5 million sessions from the subscribed users. And we use the sessions from the subscribed users to build the navigation graph. Why we use the subscribed users? Because the user, when the subscribed user visit the article, they don't have the paywall presented, so they are free to navigate. So their path is long. So we only want to know the article relationship. Yeah. So the subscribed user is very good to build to do that. Okay. And for those sessions, we further split into the training side and the testing side. Okay, the testing we pick up those sessions with a minimum length of 10 articles as the testing data, and the remaining sessions as the training data. And the training data is basically using to need to build navigation graph. There's no other learning involved. Okay, and so in our evaluation, we compare our method with 3 baselines. So the first baseline is the most popular paywall method, which is the fixed baseline. Okay, so giving the user a maximum of T articles to read. And the second one is average threshold method. So this method do not look ahead at all. It's basically based on the current state, okay, to determine. So if this resource is less than a threshold, then we just present the paywall. Okay, otherwise we allow user to continue. Okay. And so this threshold is determined as the average ratio of utility to cost over the sessions in the training data. So this is actually determined by the training data. Okay, it's not by the user. And the third baseline is same as this policy, this decision process, but the threshold is determined using a stochastic search. Okay, basically using this method, infinite difference gradient method, to search for the threshold instead of using the average. Okay, so decision function is the same. Okay. And in our method, we need the utility and the cost, right? So in our experiment, we define the utility article. We have two utility models. The first is based on the dwell time. So it is the total dwell time by all users on this article. Okay, so the utility of our article. And this is the total dwell time of all users on this article divided by the total number of visits of article. So this is like a average dwell time. And the AC model is based on the number of visits. So it is a total number of visits of article A before subscription and the total number of visits of this article. Okay, and the cost of, we don't have the money monetary amount of the article cost by paying the author. So we use the length of article as a cost. We assume the longer the article, the more expensive the article is. Okay. And the performance measures. So this is a new problem. There's no performance measure. So we have to propose the performance measures. So the first performance measure we propose is policy performance. Okay. So it's basically, let's say we have 10 testing sessions in our testing data set, and the QI denote the sequence of articles before the paywall is presented in the ICE test session. Okay, and the paywall performance measure is defined as this is the sum of all the utilities of the articles before for this test session QI before the paywall is presented, and this is the sum of the cost of the articles before the paywall is presented. Okay, and this is sum over all the testing sessions and divided by the number of testing sessions. So like the average. The average this utility and the cost ratio. Okay. And the utility model, it can be either the dwell time based or the number of visit based. So EC or AC we defined in the previous slides. And the second performance, the policy performance at different percentages article different percentages of articles delivered to the user. Okay, so when we go through this testing session, at a different point, the different percentage of articles delivered to the user, and we want to measure the data performance, the same performance at a different percentage of article delivered to the user. It's like a precision at different recurring information retrieval. Of course, the higher, the better. Okay, and the third performance measure is the percentage of active sessions at each time point. Okay, so if the higher the percentage of active sessions, the better. This is because if the paywall has not presented to the user, that means the utility to cost ratio is low. Okay, so that means the our decision to allow the user to read or not reading the article is effective. We're keeping this low. So the more sessions are going on, the more engagement we are doing for the user. Okay, so those are the three performance measures. And here is the result. Okay, so this is the policy performance for different methods. So these three are baselines. This is our method, look ahead policy. Okay, so you can see that for both utility models, our method is better than these three baselines. Okay, and this is the second performance measure. So the policy performance. I think this one is still the first one is with policy performance with respect to the maximum number of articles allowed to visit. Okay, so so for the fixed policy method, it is the T. Okay, so this number is the T. That means how many articles will allow free articles will allow readers to read, and for our method is the length of the path, the navigation path we generated, random path we generated. Okay, so so we can see that this is our methods, and those are the baselines. So you can see that for different keys, especially when t is greater than 3, then our method performs the best. But when t is smaller than 3, our method is not as good as the sum of baselines. This is because if we do not, because this is a look ahead the period, right? If the look ahead period is too small, then our prediction is based on not too much future data, right? So our decision that we make, it may not be that good. Okay, so as long as the look ahead period is long enough, more than 3, our method is outperform the baseline method. And this is a second measure, so the policy performance versus the article delivery percentage. So this is again our method. Those are the other measures. So again, then when the percentage is reasonably big enough, our method is better than those baseline method. And this is shows the percentage of active sessions at each time point, and this is the average number of active sessions. And you can see our method is better than these 2 baselines. And here is also so that our method is better than the other 2 baselines. Okay. And so we also, as I mentioned before, we can use reinforcement learning. This is because this formula is a very sequential, the decision-making problem is a popular solution is to use reinforcement learning. So after our work on this look-ahead method, we investigate whether reinforcement learning can be used to do this job. And so we further developed a Q-learning-based method. Q-learning is a type of reinforcement learning method, and to learn this action value function, which is called the Q function. So given the status and the action, what would be the value of this action given this status? Okay, the higher the value, the better this action is given this status. Okay, so I don't have time to talk about this Q-learning, and in order to do so, we need to represent the articles using numeric values. So we do that through graph embeddings. Okay, and we use the time difference method to do the Q-learning with the flip buffer and the target network and also the current network. And this Q-learning method was published together with the extended version of the look-ahead method were published in the TKDE journal. Okay, and this is the comparison between the look-ahead method with the Q-learning method. Okay, so QP is the Q-learning method, and for the this shows the active number of percentage of active sessions given the time t. Okay, so this is a look-ahead method. This is a Q-learning method. This is 2 other baselines. So this shows that the look-ahead method actually outperformed the reinforced the Q-learning method. Okay, and this shows with respect to the timelines. Actually, at the beginning, the Q, the Q learning method can do a bit better than the look-ahead method, but the overall look-ahead method is better, is the best among all methods. Why it is at the beginning it is doing better is just because Q-learning because Q-learning is trained offline, so it's a trained function. Okay, so it does not really depends on if the time is short. it does not really matter that much. But for look ahead method, if you only look at a very short period of time, it do not have much information to outperform some of the other method. Okay. However, in terms of the prediction time, this is the Q-learning method. Prediction time is fixed because the Q-learning method based on neural network, the value function is the neural network function. So so it is doing prediction is pretty fast, but for look ahead method, we have to do online sampling. So it takes time to do the online sampling, but the time is taken is linear with respect to the length of edge. Okay, so it's not that bad. Okay. So, so let me give you some summary of this piece of work. So we defined a new problem of adaptive paywall, and we developed two solutions for the problem. One is a sampling-based look ahead policy method. The other is Q-learning-based method. And the experiment showed that both methods outperformed the 3 baselines, and the look ahead method generally performs better than the Q paywall method if we compare these two new methods in terms of policy performance. Okay, and the paywall method, but paywall method is faster in making decisions. So for online inference, Q paywall is faster. Okay, but the performance is not as good as the look ahead method. So I guess I take too much time to conclude on my talk. So I have been presenting two pieces of work we have done on user acquisition and engagement. And this is critical for online news media. And the two pieces of work, first is time-aware subscription prediction, and the second is adaptive paywall. And finally, I just want to mention the impact of our work. And I actually mentioned earlier, this idea of adaptive paywall, we were the first to present it, and the idea was adopted and further developed into the adaptive paywall mechanism in the Global Mail. They have a more type of data than they gave to us, so they use more information and to build the adaptive paywall mechanism inspired by our the adaptive paywall algorithm. And this paywall mechanism lead them win a few media awards, such as this award, and also increase their reader base, so they increase their subscription rate. So and also our other piece of work also incorporated into their systems, such as dwell time prediction we did earlier, and the news recommender systems. Okay. So so that concludes my talk. I guess I take too long time, and these are basically the 3 articles related to today's talk that we published. And I would like to thank all the contributors. So Heather, the main contributing of the 2 pieces of work I talk about, and Zena contributed to the Q-learning method. And of course, we collaborate with Global Mail, and Golden is the director of their data science department. So this project is funded by the Global Mail and NSERC, which is Federal Funding Agency of Canada, and also an Ontario Research Fund. Thank you very much. So now I guess I can answer questions. Sorry for taking too long.
Okay, thank you, Professor Aijun An. Okay. So, any question for the audience?
Thank you so much, Professor. And could you explain more about the AC and EC mode model?
Oh, okay. Sure. So let me go into that.
Yes.
Yeah. So this is the different way we represent utility of our article. We want to measure the usefulness, the utility of the article, right? So one way to model is to use the 12 time the user spent on this article.
Yeah.
12 time is it's basically the time the user spent on the article. So it equals to the total dwell time by all users on this article divided by the total number of visits of this article, like average dwell time on this article. And the AC model is based on the number of visits of this article before the subscription. Okay, so if the user visits, the user have many sessions, right? In some sessions, user did a subscription, and if in that session the user visit this article, then it counted towards this numerator. Okay, and this is divided by total number of visits. So this number is very small. The number is very small. Yeah. Okay.
Okay. And do you want to compare EC model or AC model? Do you want to compare in this objective? You would like to compare?
Oh yeah, that's a very good question. So I was trying to see it look like this one is better, but this performance, remember the performance of using EC. So it's basically they are different unit, right? So the performance measure using also need the utility using EC. Yeah. So they are not comparable actually. Yeah. So maybe we can compare using the other measures, right?
Okay.
Yeah. Let's say the active sessions at each time point, right? So this seems to be the EC model is better than the
yes.
Yeah, that's a good question. I was thinking how to compare them. They say, yeah, I guess in this method we can compare them, right?
Okay, yes. Okay, thank you.
Yeah, you're welcome.
Okay, any question? Any question for the audience? Okay.
Good.
We have one question. Does the model generalize enough to apply to other data sets?
Yeah, that's a good question. Yeah, of course we need to evaluate on other data set, but to really see if it is applicable. But as long as we have a data set, this methodology is general, right? As long as we have the data set that telling us let us know to build this navigation graph, right? And you can define the utility and the cost in the way that is suitable for your domain. This method is certainly applicable, right? To other data set, right? So there is nothing very particular, because to only apply to this data set. So this the sessions. This is built based on the previous session data, and all the news agency have this click strings, right? Yeah, click strings. So as long as you have click strings, we can do the sampling to generate this this navigation path, and then the method can be applied. Right.
Okay.
So I see your testing set. Why you choose minimum length is 10?
Oh yeah, that's a good question. I forgot to mention. So it's just if too short, we do not allow the method to explore more options, right? To explore more options. So we particularly like the testing data set to be longer, so we have more decision point to make, right? Yeah. So
so navigational graph is the same of direct acyclic graph because it's a directional graph, right now.
Yeah, it's a directional graph from this article to the other article. So directional graph.
Okay. 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 Any question for another people? Okay. I think we use more spend the time for professor and for this talk. So
Okay. Okay. What, Professor Ann, what time is it? In Toronto?
Yeah, it is 11:48.
So
Yeah.
late. So late.
Yeah. So that's
I think
okay.
I think it
yeah.
is time for you to go to bed, right?
It's okay. No
Okay.
issues. Yeah.
Okay, yes. Okay. I would like to thank so much for your interesting research, right? Okay.
Yeah, you're welcome. It's my pleasure to give.
Especially in the second topic slide. Okay. I appreciate so much.
Oh, great. Yeah, hope it's useful.
Well, good.
Yeah.
Okay.
Okay.
Yes.
Before we stop the special talk, so we want to take a camera, take a photo with professor and everyone to join this special event. So
Should I stop sharing? I can stop
yeah.
sharing.
So could everyone open your camera and take a photo with Professor Ann? Okay. Okay. Moment, please.
My.
Okay. Okay. Okay.
Good to see people.
Okay, thank you so much. Thank you so much, Professor Ann.
You are
Okay.
very welcome.
I think next time you can join us again. Okay, next time.
Yes, sure, certainly. Yeah.
Thank
Most
you.
people will find this topic interesting.
Yes, thank you so much.
Okay.
Do you have planning to come to visit Thailand?
Yeah, that's a good question as well. I haven't been to Thailand. Look forward to have a opportunity to go.
Okay. Okay,
Yeah,
next time you can join us.
Yeah, let's see. Yeah. So yeah, thank you for inviting me to give this talk.
Okay. Okay.
Okay. I think everything is okay. Okay. On behalf of our department, thank for Aijun An, head of Department of Statistics, and Professor Aijun An to join the special event in here, and thank every people to coming this event. Okay. Okay. I think this time to finish the special.
Okay. Okay, thank you so much, Professor Ann. Okay, see you next time. สวัสดีครับ Thank you so much.
Bye bye.
Okay, thanks. Bye bye.
Thank
Bye,
you very
everyone.
much.
Bye bye สวัสดีครับ Thank you so much.
สวัสดีครับ
Welcome. Bye bye.
Okay.